Welcome back to our video module on dynamics. I've gone ahead and reorganized the material we've covered thus far on path basis vectors for easy reference as we explore today's problem. Today, I'd like to imagine that we have a wheel, and that wheel has a little rock on the edge of it. We'll put the rock in red, and the wheel's rolling along. So, right here, it's right there. The particle's right there. A little bit later, the wheel's rotated. It's rolling along like this and moving along. We'll say it has a non-slip condition. So the wheel's just moving along, rolling. And I want to know, maybe a little bit later, it's right here. And I want to know what the position, velocity, and acceleration are for that particle. We call this a cycloid, and if you wanted to map out the path that the particle follows, it looks something like this. And in fact, we see this type of shape has all sorts of neat characteristics, so it's worth getting familiar with today if you don't already know how some of the neat characteristics of cycloids. And as general reference, the equation for a cycloid is r equals t minus sine t in the I direction plus 1 minus cosine t in the j direction. Now in this particular case, we look at the velocity moving, the way everything's going, and you can just think your way through it. And if you do that, you'll find that the given position of that point is vt minus r sine of vt over r in the I direction plus r minus r cosine of vt over r in the j direction. This is our equation of position as a function of time in the I and j directions. Let's figure out how to identify the position, velocity, and acceleration of a particle in this particular type of cycloid motion. First, let's scroll up. Now let's take a look back and think about how we're going to attack this problem. We're given position as a function of time. From that, we can easily find the velocity as a function of time. Now remember that this velocity is going to, right down here, we'll say it's going to be in terms of I and j. And in order to understand the acceleration, we're going to have to convert that to some sort of path basis vector. The easiest way to do that is to go from velocity to the tangential unit vector. Let's go ahead and number these equations. We'll call this equation 2. We can do that from equation number 2. Here we can do two things. If we wanted to find out the tangential velocity, we could use the dot product of this term right here and this term right here, and we'd end up with some tangential velocity. This is basically looking at equation 7. Or if we wanted to find the acceleration, we could do basically the same thing using equation 6, and that would give us the tangential acceleration. We're basically looking for this term, and the way that we're going to find that term is taking the overall acceleration and dotting it with the tangent unit vector. Now if we have the tangential acceleration, we can use equation 6 to find the normal acceleration, and the easy way to do this is from our initial diagram, we can find the acceleration very easily. We can find the tangential acceleration really easily. We just subtract, and what we're left with is the normal acceleration. Finally, we can use the quantity of the normal acceleration, put that into vector notation by noting that it goes in this direction, divide by its magnitude, and there we have the unit vector in the normal direction. Finally, if we wanted to find the osculating radius, we just go back to equation 6. We know this total term. We know E of n, or we know En, we know v squared, so we can just find rho. That's equation 6. In summary, we start off with position. We then use the velocity to find out the tangential unit vector. We find the tangential acceleration, use that to find the normal acceleration. With the normal acceleration, we can find the normal unit vector, and we have pretty much all the information we need. Let's scroll down and see what this solution looks like. And for the purpose of this example, we're looking for the velocity and acceleration that a particle feels when it's at the top of its path. So here we see what the math looks like as we follow that structure. We start off with, let's follow along in yellow. We start off with our position. We then go to our velocity. And while I was doing derivatives, I went ahead and found the acceleration as well. Next, I used the velocity here at this particular point. This is the point when we're at the top. Velocity times the time equals pi r. We say that the velocity here is simply 2vi, and if we use our equation equating et with the direction of the velocity, we see that we have a really simple conversion here. Et equals I. Next, we look at our acceleration. The reason we're doing this is because we want to understand En next. We see our acceleration is in the negative j direction. Don't forget that negative. First, we ID that the tangential acceleration is the acceleration in the tangential direction, or in the et direction, and that's going to be 0. Notice that the remember, et is in the I direction, and here we have an a in the j direction. So that's going to be 0, which means our total acceleration is purely in the normal direction. We know the velocity. Now we can use the total acceleration in the ij coordinates and the total acceleration in the en coordinates, and we can equate them. We know that if we look at the unit vectors, we can get a relationship between the two, and we see that En is negative j. There's that negative sign. Finally, we want to come up with some sort of relationship between rho and the actual radius of the circle. So we know these numbers have to be the same. So up here we know the direction of the equation has to be the same. It's a vector-based equation. And we also know the numbers have to be the same, so rho equals 4r. What does that look like in our current setup? That means that the oscillating radius is 4 times the size of this circle right here. See, 1, 2, 3, 4. Yeah, it would look something like this. And you can see where the osculating gets its name. You can see how these just kiss right here. If we say that the red is the path that the pebble takes, the yellow is the radius that the particle feels at that space. Finally, if we wanted to look at what this might look like in the velocity would look like in ET form or in the EN form, we have that right there. The important takeaway from this is you get a chance to see how we use these equations in a real problem. In summary, we were able to come up with a basic approach that we would take so that we would find out really what we're looking for is En, Et, and we'll need the osculating radius, looked at how these equations relate, and we were able to try it out on problem. I hope this gives you a good feel of how to use path basis vectors while evaluating constrained motion problems.